Hey everyone, welcome back to TechBit Academy. Please like this video and subscribe to the channel.
Welcome to the Explainer. So, today, we're going to pull back the curtain on what's honestly the ultimate technological magic trick. And it's happening right behind your screen, literally every single day. You know, we interact with these digital systems constantly, completely oblivious to the staggering complexity that makes them tick. We click a button, boom, things happen. But how does that actually work? What are these systems hiding from us to make the experience feel so incredibly smooth? Well, let's dive in and find out.
Think about the app you're using right now, or say the cloud storage you've saved a file to this morning, even the streaming platform you watched last night. It feels completely self-contained, doesn't it? It feels like you're just communicating with one unified entity. But are you actually using just one computer? In reality, no way. Loading just a single modern web page can require your browser to talk to dozens of different servers scattered all over the globe. So your experience tells you one thing, but the engineering reality, it tells a completely different story. And that right there sets up our whole central premise for today.
All right, part 1, the single computer illusion.
You see, the modern network's greatest achievement isn't actually speed or even storage capacity. It's really a masterfully crafted deception. To truly understand this deception, we have to look at the contrast. On the left side, we've got the messy reality. Data, processes, resources, they're physically distributed across multiple computers. We're talking different racks, different data centers, maybe even different continents. It's a highly fragmented, chaotic reality. But on the right side, that's what you actually experience. A single, seamless computer system. Bridging that massive gap between a messy reality and a perfect perception, that is the absolutely crucial job of a distributed system.
And that brings us to our central definition. Look at foundational engineering literature and it'll tell you an important goal of a distributed system is to literally hide the fact that its processes and resources are physically distributed. When a system successfully presents itself to users and to applications as if it were only a single computer system, it's said to be transparent. Now, in computer science, transparency doesn't mean you can see everything. Actually, scratch that. It means the exact opposite. The system's inner workings are totally invisible to you. It's perfectly transparent, kind of like a flawless pane of glass. You don't see the glass itself, you just see the view.
Moving on to part 2, hiding access and location. Geographic invisibility.
So how exactly do they pull off this invisibility? Well, the first trick in the book is called access transparency. In the real world, different computers use different operating systems, different file structures, totally different ways of representing data. Without access transparency, you'd have to manually translate your request depending on the exact type of server holding your data. Sounds like a nightmare, right? But the system translates all that gibberish behind the scenes. It completely hides the differences in data representation and exactly how a resource is accessed. It handles the whole shebang, so your file is just handed to you perfectly formatted.
Next up, we've got Location Transparency. This one's all about geography. It means the system completely hides where a resource is physically located. Think about a web address. When you type in a URL, you definitely don't need to know the GPS coordinates of the server building or which specific hard drive and which specific rack is giving you that web page. The system maps your simple request to a physical location completely invisibly. You never need to know the actual geography. The physical location of the resource, totally hidden from you.
Okay, part 3, moving resources invisibly.
Now, data isn't static, which brings us to migration transparency. This rule dictates that the system has to hide the fact that a resource may move to another location. Say a server is getting too hot or a hard drive is hitting its capacity limit. The system can just pack up a database or a file and physically move it to an entirely different server on the other side of the country. And because of migration transparency, you, the user, never notice the shift. The resource still has the exact same name and acts the exact same way. Pretty cool for sure.
But let's take that a step further with Relocation Transparency. This is an absolutely incredible feat of engineering. Relocation Transparency hides that a resource may be moved to another location while it's in use. Contrast this with basic migration, where, maybe the system moves a file while you're asleep. Relocation Transparency is literally like a mechanic changing the tires on your car while you're actively driving down the highway at 70 miles an hour, and you don't even feel a bump. You're actively interacting with that exact resource, streaming a video, editing a document, and the system physically pulls the resource out from under you, moves it to a new server, and reconnects it without skipping a single beat. It's mind-blowing.
Part 4, managing copies and competitors.
The illusion gets even deeper when we realize you're rarely the only person using a system. And honestly, there's almost never just one copy of your data. This requires replication transparency.
To make systems fast and reliable, engineers will often create multiple copies of the exact same data and spread them all out. If you're in Tokyo, you pull from the Tokyo copy. If you're in London, you pull from the London copy. But the system strictly pretends there is only one. It entirely hides the fact that a resource is replicated. Say you update your profile picture. The system updates all those hidden copies in the background, but to you, it just looks like you changed your one single profile.
And then we have concurrency transparency. What happens when multiple competing users, or applications, try to access the exact same resource at the exact same time? Without this transparency, files would get locked, data would get overwritten, and you'd constantly be told to, hey, wait your turn. But concurrency transparency hides all of this. It hides the fact that a resource is being shared by several competitors. It manages that queue in the background so flawlessly that every single user feels like they're the absolute center of the digital universe with exclusive, dedicated access to the system.
Which brings us to Part 5, the art of invisible failure.
Finally, we reach what is arguably the most crucial magic trick of them all. Look, hardware crashes, cables get cut, the power goes out, it happens. But a truly transparent distributed system possesses failure transparency. It completely hides the failure and the subsequent recovery of a resource from the user. Imagine a chef dropping a dish in the kitchen, but instantly cooking a brand new one and placing it on the counter before the waiter even notices. The user just experiences a slight, barely noticeable pause. Meanwhile, in the background, alarms are ringing. Backup servers are booting up. Data is being totally rerouted, but the facade, flawlessly maintained.
So when we bring it all together, we get a complete visual cheat sheet of the whole operation. To maintain the grand illusion of a single computer, a distributed system has to orchestrate these 7 distinct types of transparency. It hides access differences in location, it hides migration and active relocation, it masks replication of data, manages concurrency among users, and completely paves over failure. When all 7 of these are working together in perfect harmony, you get the seamless digital world you interact with every single day. It's just an absolute masterclass in technical deception.
Which leaves us with one final, kind of provocative thought. We've seen today just how much immense complexity is hidden right behind your screen. We demand systems that are fast, reliable, and perfectly transparent. But when a system is designed to hide absolutely everything so perfectly, what happens when the illusion finally breaks? Because when a system this wildly complex finally fails loudly enough for the user to actually see it, it usually means the magic trick has truly run out of sleight of hand. Keep that in mind the next time you click a button and expect a seamless response. Thanks so much for joining me for this explainer, and keep questioning the reality behind your screen.